The other situation that momentum is really good for dealing with is the opposite of collisions. Instead of two objects coming together, you have one object flying apart into two objects or more. That's an explosion. For those of you who have fired a gun before, you felt a recoil, right? Kind of a kickback. And that's due to the conservation of momentum. So first, let's look at a simple, just a simple weapon being fired. This is my cannon. I know it's not good. It has a cannonball of mass little m inside of it and a mass of big M for the rest of the cannon. And it's sitting there, completely at rest. And then it fires the cannonball out. We'll say that it fires the cannonball with a speed of v to the right. Cannonball has mass little m, cannon has mass big M. And I want to know how fast does the cannon kick back? So we know this cannon should be moving to the left. You can say it's moving to the left, and with u, and you want to find that, and you'll get a positive u because you're already counting for direction, right? But I kind of prefer to assume that everything is moving to the right, even though I know it's not, because that way, and I want to find this u, which is a vector here, and that way if I get a negative sign, I know, oh, it should be to the left. So that way, positive always means right, negative always means left. Otherwise, if you get a negative sign, if you try to guess the direction, a negative sign means you guessed the wrong direction. Okay? So, because I'm kind of working with the plus-minus coordinate system. So, this is just a conservation momentum problem. My initial momentum over here is 0. The cannon's not moving at all. My final momentum here is going to be big mu plus little m v. And I want to find u. So I set these two things equal. Pi equals Pf. 0 is equal to big M times u plus little m times v, which means that solving for u, we get that u is equal to mv over m negative. Little m over big M. And this means that this cannon is going to be moving with, where do I want to write this? So u equals little mv over big M to the left, which we knew was supposed to happen. So that's good. You can also check this because if the cannon is way more massive than the cannonball, right? Let's say this big M is much, much larger than the little m. Well, in that case, this term becomes 0. If this big M goes to infinity, this term becomes really, really tiny, which means this experiences almost no recoil, which is what you'd expect if you have a huge, massive object firing a very small, not massive object in the opposite direction. Good. So this is you're always going to do the same thing. Same steps as inelastic collision. Find the initial, find the final, set them equal, and solve. You're done. Explosions can get trickier, though, when you have more than just one dimension that they're being fired in. So let me give you an example. Let's say I have some kind of explosive moving to the right with an initial velocity of v. And let's say it has a mass of m. And then all of a sudden it explodes. I don't know why, it just does. So after it explodes, you're gonna, let's say it blows up into 4 pieces. Let's say I tell you that this piece has a mass of 1/4 little m, and it's moving, actually let's say it's 1/8 little m, and it's moving to the right with a speed of 2v. Let's say this one has a mass of 2/8 m, and it's moving down with a speed of v. And then this one has a mass of 3/8 m, and this has a mass of 2/8 m. Okay? So I want to find what is u1 and what is u2. So again, I'm going to assume, and I didn't draw this arrow correctly here, I'm assuming everything is going to move to the right. Okay? Because that way if I get a negative, it means that, oh, I picked the wrong direction, it should actually be to the left, or it should be down. Because here we have the 2 dimensions. So up will be positive, down will be negative, right will be positive, left will be negative. Okay? But you do have to take into account, I tell you this object is moving v down. So you have to incorporate the negative sign for the direction here, because you know it. Here I don't know it, so I can do whatever I want. So to solve this you might think that you have to add up all the pieces and set it equal to its initial momentum. But in fact, momentum is conserved along any given axis. So momentum along the x-axis is conserved, and momentum along the y-axis is conserved. So due to this fact, we're able to actually find u1 and u2. Otherwise, if we add up everything, we have two unknowns and we can't solve it. So the fact that momentum is conserved in the x direction allows us to set initial momentum in the x direction equal to initial momentum, final momentum in the x direction, and initial momentum in the y direction equal to our final momentum in the y direction. So setting up these two equations, the initial momentum in the x direction is equal to mv, right? So we're going to have mv, this is the x, mv is equal to, well, I have 2/8 mv, and then I have plus 3/8 mu, right? I want to find what u is. So I can get rid of the m's here, right? I can subtract 2/8 v from both sides, so I get 6/8 v is equal to 3/8 u. Multiply both sides by 8, divide both sides by 3, u is equal to 2v. Now, this is interesting. This says that this object actually is moving to the right, which maybe isn't so surprising, because if you think about it, I'm calculating this frame, this explosion, from the point of view of somebody who's watching. And if I throw this marker, and this marker explodes, even the back piece that exploded kind of away from where the center of mass was, it's going to maybe still be moving forward. If I was in the same frame as the marker, then maybe it would be moving backwards. But u equals 2v, or this was u2. u2 equals 2v. Okay? So u2v to the right, so we pick the right direction. For u1, we have to set up our equations for the y direction. So our y direction equations is going to be, well, the initial momentum is 0. So 0 is equal to the y direction, which is 2/8 mu1. Minus, because this one is going down, so we have minus 2/8 mv. So this is actually nice, because we can just look at this and say, oh, these have the same masses, must have opposite velocities if it's going to be 0. So u1 has to be equal to v, but in the other direction. And we can go through and solve this and say, okay, well, all of these cancel, so we're left with u1 equals v. And note that it's positive, which means it's moving up, which means we chose the correct direction there. And that's how you solve two-dimensional explosions, at least that are along perpendicular axes. If you have a situation where maybe a piece moved up to the left and this way at an angle, let's say an angle of theta, then you can't do it as straightforwardly as you could here. Because then what you have to do is let's say this is the momentum of p, you have to break this into the x component of p and the y component of p, which just involves some trigonometry. But that's how you solve explosion problems. The key is just remembering that momentum is conserved along any given axis.